Over to you, sir.
Thank you very much. I'm Andrej Il'ichev from mathematical from Steklov Institute from Moscow, and first of all, I'd like to express my gratitude to organizers of this workshop for giving me opportunity to participate. The talk will be devoted to the nonlinear wave patterns, steady traveling waves bifurcating from the quiescent state, and that talk will be in a spirit of the previous talks by Professor Van den Broek, and we try to describe the local families of solitary wave analytically, bifurcating from the quiescent state beneath the ice cover. Of course, the form and the propagation properties of such waves, in our case, firmly depend on the model which we use for their description. And in this case, we use the model for water as complex as we can. But for the ice cover, we use the slightly simplified model, the model of the ice sheet of the ice plate, of the elastic plate, Kirchgoff-Love elastic place. I understand that ice itself behaves not like the elastic plate. It can be inhomogeneous, can have in particular various thickness, but the simpler model we use, the more analytical results we are able to get. For the description of the wave propagation in the fluid, we use 2D Euler equations of non-viscous fluid, and coupling these, so this model is frequently used in the description of the process, and we are able to get some solutions, some families of solutions, not solutions, but families of solutions, solitary waves of different kinds, dark solitons and so on, analytically, describe them, their form analytically. First I give the formulation of the full formulation of the problem, then I describe the running waves and the main parameters which appear in the problem. There are three, the parameters to be varied. Then the significant thing in our analysis is the change of variables which makes it possible to map the unknown domain of fluid flow to the strip. Then we consider the equations on the strip and the bifurcations which are governed by these equations. And the central part of the discussion will be center manifold reduction. We project the center manifold is the place where the local bounded solutions live, and we project our system to the center manifold, which helps us to reduce the infinite dimensional dynamical system to the finite dimensional dynamical system and investigate it by the either normal form analysis or by any other methods. As an example, we consider simple resonance, which gives us, which gives us the solitary waves of depression. The solitary waves of elevation do not exist in this case, because we have the additional surface effects, and they are replaced by the so-called generalized solitary waves, which existence is connected with the process, the non-stationary process of localized of localized perturbation elevation. Radiation. The existence of non-localized generalized solitary waves lead to the radiation process for the localized perturbation Then, of course, envelope solitary waves and so-called dark solitons, which are actually the product of the nonlinear product of the Bohr and periodic solutions. And we finally consider the critical parameters which correspond to the replacement of envelope solitary waves by dark solitons, namely the replacement of self-focusing region by defocusing region. And the literature devoted to the question of the surface waves is vast and very deep. And of course, we have to remember the Russian scientist Lavrentiev, who started this history and who first proved the existence of solitary waves of elevation on the clean wave surface. Then we may speak about results of Fredericks and Hires, the global theories Amick, Amick-Toland, Amick-Turner, Frankel, and many others. I mentioned here only the papers which is closely related to the topic of the present talk, and they are the papers of Jos and Kirchgoff in 90th, where they considered the case of the surface tension, and they give the description of generalized and solitary waves and envelope solitary waves families locally, bifurcating from the quiescent state. These families parameterized by small amplitude. Then we should mention also the paper by Diaz and Dios, where they described the envelope solitary waves in the surface tension case. And finally, maybe I have to mention the paper of the solitary waves on the interface, dark solitons on the interface of two fluid system with surface tension, because in this paper the authors found the family of so-called dark solitons, and in our case, and as it was mentioned in the previous talk, we have also dark solitons which correspond to the behavior of the leading of the coefficient at the leading nonlinearity of the problem. I should say that the waves bifurcating from the quiescent state in the case of flexural gravity, presence of elastic plate on the surface, or capillary gravity case are qualitatively similar. But of course there are differences between these two phenomena. The scales are different. If for solitary waves with surface tension we can speak about millimeters, a characteristic value of the amplitude about millimeter, and so these waves are invisible because they are destroyed by damping process. The small amplitude and the viscous effects are very strong on these scales, but the waves in the flexural gravity waves, the scales of these waves are up to 1 meter, and of course the model of the perfect fluid in this case is more or less adequate, and we can see, and I speak about it later, these waves in practice. So the formulation of the model. We are in the region occupied 2D case. We consider we are in the region occupied by fluid with two coordinates unbounded and bounded, and this region has two boundaries, the bottom, the horizontal bottom, and the unknown upper boundary, where the ice plate is freely floating. The equations are the following, are the usual. So the equation for potential in the domain, then boundary conditions, and in our case, unlike the case of the previous treated in the previous talks, we consider the usual Kirchgoff-Love plate, not shell, Cosera, and so the additional pressure caused by the presence of this place is given by the second derivative of the curvature, or sorry, of the curvature here, and this term corresponds to the press stress in the ice sheet, initial press stress, tension in the ice sheet, and it gives the analogy with the case of the capillary gravity case, though the order of the equations are greater than in the case of gravity capillary case. Here constants B is that corresponds to the initial tension. C is actually the inertia, the inertia coefficient of the ice plate, which is also taken to consideration. K is the curvature of the ice plate. Here we have the additional term, which is proportional to the thickness, the ice thickness introduced by Forbes in one of his papers in 80s in Journal of Fluid Mechanics. And this is the second derivative of the curvature, is the additional pressure caused by the presence of the plate. As usual, we need we consider the traveling waves to the left, and in the system firmly attached to the traveling wave, we can stop this wave, and the fluid will run to the right. And we in non-dimensional variables, the equation governing the propagation of steady or traveling waves have the following form. Here the unknowns are the velocity, two-dimensional, and the surface elevation or deviation, and B is constant lambda, is the inverse square of the fruit number. B is the analog of the bond number in the case of surface tension. Gamma is dimensionless flexural rigidity. Three main parameters, lambda, B, and gamma, to be varied further. Strictly speaking, the velocity will be varied, and therefore these three parameters will be varied. C is the parameter corresponding to the inertia of the ice. K is the ratio of the ice thickness to the depth, and these two last parameters are fixed. And K are the corresponding second derivative of the curvature and curvature itself, K1 and kappa 1 and kappa 2. And which is important, we need to make mapping from our unknown domain to the strip 0, 1 of the width 0, 1 of the width 1, and this mapping is performed with the help of the stream functions. It's not my result, of course. It's previous result. It seems to me by Milke. So he introduced new coordinate stream function, which this transformation is local. So we consider the waves of small amplitude near the quiescent state. Therefore, we may be sure that this transformation is invertible, and this transformation maps our unknown domain of the flow to the strip r times 1, 0, 0, 0, 1. And after this transformation, the usual velocity transforms to the new velocity v1, v2, coming to 0 at infinity. And as I said, the mapping is invertible, locally invertible. The mapping is local, and it is invertible. I underline one more time that we are looking for the local families, for the beginning of the families of the waves bifurcating from the quiescent state. So the deviation of our now we speak about a little about the equations on the strip. The deviation, the unknown deviation of the water-ice interface expressed through the average of the first component of new velocity. U is 5-component vector of unknowns. Lambda bold is 3 main parameters of the problems to be varied further, and it could be seen that the system of equations can be written in operator form and as infinite dimensional dynamical system, and dot denotes the differentiation in this case with respect to unbounded variable, and A is the linear operator, phi f is the vector function of vector functions corresponding to the nonlinearity of the problem, and mu is the parameter, the bifurcation value, so-called, which is the deviation from the critical value lambda 0. So A is the operator from its domain to some space functional x, and x is R3 times square integral functions, and the action of A is shown here. S1 and S2 are the corresponding to the first and the second derivative from S0 to be specified below, and the domain of the operator A is R3 times square integral functions and their derivatives also, and S0 is expressed through the trace of the second component of new velocity on the upper bound of the strip. So our equations now are in operator. Our equations are in operator form, and we verify. We change the value of speed in a manner that the parameter corresponding to the fruit number change as follows here, as shown here. So this is bifurcation value, small enough, and due to this change, can be computed the change of velocity and the change of this second b and the third constant, main constants of the problem. Next, we can write the bifurcation relation of the problem, and we are deeply interested in those values, eigenvalues of the operator. Sigma is eigenvalue of the operator A, and we are interested in these values which are coming to the imaginary axis due to the fact that we have in the problem unbounded direction, horizontal direction. The problem is itself conservative one, so we have the intrinsic symmetry. The intrinsic symmetry is connected to the fact that properties of the unknown variables are the same in both direction, negative and positive, of the unbounded in the unbounded variable, and this system is therefore reversible. It is called reversibility property, and the eigenvalues of the operator A come to imaginary axis in pairs, and when they come to the imaginary axis, the bifurcation occurs, giving rise to the appearance of the new families of solutions. And we can consider the parameter space lambda, beta, and gamma. The main parameter space, three parameters: fruit number, bond, the analog of bond number, pretension parameter, and dimensionless flexural rigidity. In this space, we can plot the so-called critical surfaces. One of these critical surfaces is the plane lambda equals to 1. The other critical surface is the surface. I show the equation of this surface where the group velocity equals to the phase velocity. On these surfaces, the eigenvalues of the operator A come to imaginary axis, and bifurcations take place. Slightly above the plane lambda equals to 1, we have the visible eigenvalues coming to 0 on the critical surfaces are driven by are pictured by black, and above the plane and at both sides on sigma, and the eigenvalues which are not visible for us pictured by white beneath under the plane lambda equals to 1. So we have three regions on the surface, on the critical surfaces, which I repeat, they are plane, and the other critical surface is sigma. The first, the plane is arbitrary beta and gamma, and lambda equals to 1. So the characteristic wave speed equals to the characteristic speed of linear waves. And here is the typo beta greater than 1/3, and gamma is flexural rigidity and always positive. The other region bear less the small or zero or negative maybe restraints gamma also greater than 0, lambda equals to 1. It is the region under the surface, the plane lambda equals to 1. And the third region is the whole surface sigma, which is given by the following equation. So the parametric equation lambda bear and gamma and q, the dimensionless wave number varying along this surface. So this I repeat, this is the surface where group speed equals to the phase 1. And due to the different eigenvalues behavior in different regions, which are shown here, we get the different wave structures appearing, wave families appearing from the quiescent state. So the most important point of our discussion is center manifold reduction, and this corresponding theorem was proved by Milke in 1988. It says about the following: let we decompose the infinite dimensional solution U into two parts, finite dimensional and infinite dimensional. A0 is restriction to the finite dimensional space and A1 to the infinite dimensional span. Then when the operator A have some properties, in particular it is closed, we have the so-called center manifold. So we can express, non-linearly express, the infinite dimensional path through via the finite dimensional path. Mu is the bifurcation value, is small enough. Besides this, so we may restrict our infinite dimensional equation to the finite dimensional equation, because U is a function, nonlinear function of U1 of U0, center manifold. Moreover, the nonlinearities and the operator A inherit the symmetries of the problem, and strictly speaking, we can write the following, but it seems to me that you ought not to read this, but there are some reversibility properties which are inherited, which is inherited by the system, the new finite dimensional system of equation. And as an example, we consider the case of the simple resonance, the first case, when the parameter b greater than 1/3 and we are on the plane lambda equals to 1. In this case, our solution may be, our unknown vector may be projected to the center manifold with the help of the generalized eigenvectors of the adjoint operator, and this finite part spanned by the generalized eigenvectors of the operator A itself. And in this case, only two eigenvalues come to imaginary axis to 0 point. And in this case, we obtain the so-called solitary waves of depression. So the deviation of the water ice surface is given by the following formula, where R0 is simply cosine minus 2 function, and it corresponds to the solitary wave of depression. And here on the picture, the solitary waves for different values. The thin line corresponds to solitary wave for the neglecting ice inertia, and thick line solitary wave to the ratio of the thickness, ice thickness, and depth is 1/10. Moreover, the equations on the center manifold, so the our unknown finite dimensional part is expressed through these two vectors, which are given on the previous slide, and A0 and A1 depends only on x, and the shown system locally corresponds to the full system of equations. So we need to solve this system. We may to solve the cut-off equation, and which gives the solution like cosine, and then to prove the so-called persistence theorem about the fact that solution of the full system is the solution of the same nature, coming to 0 at infinity, and it forms the form of the solution of the cutoff system approximates the form of the solution of the full system with respect to the amplitude, which is small enough. The other case, so it is the case when we it was the case when we are above the surface lambda equals to 1, mu greater than 0, the value, the bifurcation value greater than 0. When we are to the right of the surface sigma, in this case, we get the I'm sorry, when we are under the surface lambda, under the plane lambda equals to 1, we get the so-called generalized solitary waves, and their form, they are the non-localized wave patterns, and their form was shown in the previous talk and in talk of Emilian, but they give rise to some non-stationary process, the process of radiation, the non-stationary process, the radiation of localized perturbation. So the localized perturbation begin to radiate in this case, because it cannot find, it is not able to find a solitary wave corresponding. They do not exist in this case. So the amplitude of this tail for the generalized solitary waves is small, the smaller amplitude of the core. When the amplitude is moderate, the amplitude of the wave tail is considerable, and the localized perturbation begins to radiate wave tail, and this wave tail takes the energy from the main wave core, and in future this wave tail will be subjected to the modulational instability, periodic wave, and it is disintegrated to the so-called envelope solitary waves, non-stationary, when the group speed not equal to phase speed. But it's the separate story, and I shall not speak about that. Now, when we are to the right of the surface sigma, we get the so-called the family of so-called envelope solitary waves. Not long ago, one fellow from Arctic and Antarctic Institute in St. Petersburg told me that he detected such waves in practice, and their parameters, I mean the velocity and length, they correspond to the parameters theoretically found. By the way, in this Arctic and Antarctic Institute, they are involved in measurements connected with Arctic and Antarctic problematic, especially and particularly the ice water phenomena, and therefore they twice a year they come to expeditions, and the most frequent question that they ask is how your results correspond to the real engineering applications. So very severe people, very severe guys, but they are working hard. So the shape of this wave in the nearest order in amplitude is given by these equations. Q2 is the coefficient at the leading nonlinearity. Q1 is some other coefficient which is positive. Mu is greater than 0, and Q2 is positive in this case. But in our case, we get also the so-called dark solitons. As far as I understand, this name came from optics, when for the dark soliton, the illumination has a minimum in the point of symmetry, and this is a nonlinear product of Bohr with a periodic wave VR under the surface lambda equals to 1. The shape of these waves is given as follows. Mu in this case is less than 0, and Q2, the coefficient at leading nonlinearity, is also less than 0. And of course, all these solutions, unlike the solutions in the previous talk, are symmetric, because we are at very beginning. We only starting the branches of these solutions. The solutions to be continued with respect to amplitude with parameter mu. So here is the picture showing the Q2 coefficients behavior versus the dimensionless wave number, and we see that at some point this coefficient for the absence of the when the inertia, the ice inertia is neglected in comparison with the water inertia is neglected. But in the case when it is not neglected, the picture is similar. The picture is similar. In this point we have this coefficient changes its sign, and we have the dark solitons replace the envelope solitary waves. So the deeper, so we have here the table with the critical values, critical I shall say in what sense, values of the water depth for different ice thicknesses, taking into the consideration ice inertia, and when the fluid is deeper than the fluid having the critical depth, we have dark solitons replace the envelope solitary waves. So we have so-called defocusing process, the envelope solitary wave is itself a detector of the of the modulational instability of the basic periodic wave, and the dark soliton is a detector of the modulational stability of this wave, and the focusing and defocusing change each other when we overcome the critical depth. And as it's seen here is the thickness, the ice thickness is about 3 centimeters, 11 centimeters, half a meter, and greater Arctic regions. The depth of the fluid is considerable when the focusing changes focusing. And to finish with the table giving an example of critical depth and critical velocities and critical length in the case of the when the ice inertia is neglected, and it is seen the deeper is fluid, the thicker is ice sheet, the bigger, the greater the difference between the depth, the critical depth of the basin. Thank you very much for the attention.
A question time?
The question is, there are, for example, classic Stokes waves. Yes?
Yes.
Periodic, very nice, very old stuff. On the other hand, there is what is called central manifold technique. Yes? Stokes waves cannot be obtained, but by using center manifold technique, in principle. Yes.
Yes.
Today we have a number of very nice talk about some hydroelastic waves. You propose technique based on the center manifold method. Yes, there are different waves what considered today yearly and in your talk.
I think that the waves considered today, when they are restricted to the small amplitude, are the same as my. But in the present talk, we give the parameter domains where the different waves exist, unlike the previous talks. And of course, they are the same. But for example, in the previous talk, Professor van der Broek told us about the continuation with respect to amplitude, about the non-symmetric waves. There are waves of moderate amplitude. Here we treat only the waves of small amplitude, non-linear, but analytically, not numerically.
It is a little bit strange because it follows from this that you can give description of Stokes type waves of small magnitude, independent on period, symmetry, asymmetry, and something like this.
I don't think about this.
Take that up later.
Yes, it's a discussion.
But is there any other question?
As I remember at the beginning, you said that your plate is linear, and the non-linearity is due to
No. It is physically linear in the sense that we are restricted to small strains, but we can consider the considerable displacement, large displacements of the plate. And geometrically, it is non-linear because we are using the non-linear curvature. But physically linear, of course, Hooke's law.
How much is it important non-linearity? Because you are working with the small amplitude waves, and I noticed the order of the solutions is mu in the power 3/2.
No, mu in the first power, and
Even first power.
in the first.
So then that non-linearity some nonlinearity,
plate
they
nonlinearity,
give
or-
nothing, right?
But they are nonlinear. But of course, these waves, when prolonged, when continued with respect to amplitude,
Yeah.
the nonlinearity will play sufficient role. And it depends, the nonlinearity purely curvature or the curvature cube, and the amplitudes will be different
Ah.
in this case. And in our case, it seems to me, I suspect that nonlinearity of the plate plays no role,
Yeah.
but the nonlinearity of water wave plate equations plays role, of course.
All right, well, our time seems to have left us. Let's thank our speaker.
Thank you very much.